What is the authoritative experiment of the Monty Hall problem validating? After researching online, I discovered that people who believe in the authoritative answer have their own faith foundations. Some are convinced by the argument that there is a 2/3 chance of winning by switching doors, while others are convinced by the results of simulation experiments. Generally speaking, it is difficult for the proponents of the authoritative answer to provide effective logical arguments on the debate over the probability of the two doors, so many people eventually rely on the results of the experiment. This episode is intended to thoroughly analyze what the authoritative simulated experiment is modeling. In general, there are two forms of authoritative simulated experiments. One type of experiment simulates never switching doors and always switching doors using the same sequence of events twice, and then compares the two sets of data. The other simulation method divides the same sequence into two halves. One half simulates not switching doors, and the other half simulates switching doors. It can be confirmed that the probability of winning by never switching doors is always 1/3, and the probability of winning by always switching doors can definitely be 2/3. This is because, as mentioned in the first episode, this verifies the probability of choosing 1 out of 3 as 1/3 and choosing 2 out of 3 as 2/3. This simulation is not validating the probability of switching in a single game, but the probability of the prize repeating in two doors after multiple repetitions. However, even at this point, it seems that most people do not agree. They believe that regardless of what is being validated, the result that is consistent with their reasoning is sufficient. So now we will see what the authoritative experiment is really validating. In the Monty Hall problem, a key core premise is that each game is an independent probability event, with no relation to previous or future games. With this premise as the logical foundation, let us assume that in the simulated experiment, each guest is given a name for each game. When thousands or even tens of thousands of simulation sequences are displayed, people should realize that the results of the simulation statistics are actually the winning probabilities of the group that chooses to switch or not switch doors in a continuous process of repeated games. However, each person's name can only appear once in the entire group. The first logical point is that players participating in a single game do not have the chance to win 2 out of 3 times. The correct description is that in 3 games, 2 people may win, but it will never be the same player. The second logical point is that the winning probability of the group does not necessarily equal the winning probability of each individual within the group. The reason why the winning probability of the group is higher comes entirely from the probability combination generated by the door switching choice caused by the game rules, which increases during the repetition process. The necessary premise for this probability to double is that the selection process must be continuously repeated. Without continuous repetition, there will be no additional combinations, and the probability will not double. The fact is that each guest will not repeat participating in the game show. Therefore, the authoritative simulated experiment is not validating the winning probabilities of switching or not switching doors in each individual game at all. What is actually being simulated is the probability of the host losing the car when every guest in each episode chooses to switch doors. In other words, if there are a total of 12 episodes, the host needs to budget for at least 8 cars. In each game, the probability space faced by the guests does not include the possibility of multiple combinations. The probability space is a crucial foundational concept in probability analysis. It is actually the domain of definition for probability variables. In this domain, all possibilities related to probability events must be sufficient. As the saying goes, not one less. However, unrelated possibilities cannot be added arbitrarily, and no extra possibilities are allowed. This is the rigor that scientific definitions must possess. The authoritative answer to the Monty Hall problem demonstrates extreme confusion in the concept of probability space. The first layer of confusion arises from multiple permutations and combinations that can only occur through repeated repetition, rather than in a one-time probability event in overall probability analysis. The second layer of confusion arises from the probability calculation for the chance to choose between 2 doors. This calculation only considers the 2 door combinations mentioned in the problem description, completely ignoring the possibility of other 2 door combinations, including the combination between the last 2 doors. Therefore, it leads to an incomplete definition of the probability space. Imagine analyzing on an incomplete variable basis. How can the conclusion be correct? The third layer is, of course, the model design for the simulated experiment. Undoubtedly, the experimental model must fully adapt to the domain of definition of probability space to correctly simulate the corresponding probability results. Since the correct domain of definition does not include the multiple permutations and combinations that only occur through repetition, the redundant permutation and combination states in simulated experiments must be eliminated. There is a simple way to randomize the door-switching choices in the experiment. Although the final number of door switching and not switching is roughly equal, the resulting probability is approximately 1/2 for each of the two choices. The reason is that random selection eliminates redundant combination states that have different permutations but the same result. After several episodes of video, all the questions have basically been explained. It can be said that the concept of probability space is the most effective professional tool for testing the correctness of authoritative theory. It may be difficult for ordinary people to understand, but experts and scholars related to probability science have no reason to shirk. If you want to prove that the authoritative answer is correct, you must first prove that its probability space setting is strict and complete. If even this most basic logical foundation cannot be proven, then everything else is off the track of correct analysis. Overall, the Monty Hall problem is a very interesting and thought-provoking problem. It involves not only probability analysis, but also mathematical and logical analysis, challenging people's thinking in many ways. Through comprehensive analysis, we finally realized that the Monty Hall problem is a triple probability problem. When the player only has one chance to choose, he only has a 1/3 chance of winning. When he has a second chance to choose, the probability of winning increases to 1/2. If he can play multiple times, he can have a 2/3 chance of winning. That concludes the analysis of the Monty Hall problem. Thank you for watching.